So now let's take a look at our non-inverting Schmitt trigger configuration. So we can see our circuit below here looks very similar to what we saw for our inverting configuration. We still have this positive feedback where our output is connected to our non-inverting terminal via R2. The only difference is now we have our ground connected to our inverting terminal and our input voltage VI indirectly connected to our non-inverting terminal. Okay, so again, to help us with our analysis, we can label this voltage here as V plus. And so when I say V plus, I'm referring to this V subscript plus as opposed to our power supply, which is implied but not shown explicitly here. And so in order to get an equation that relates our V plus to our input and output voltages, we're going to use superposition and voltage divider. And so I'm not going to go through this in a lot of detail, but again, if anybody needs some extra help with this, or if you just don't see where this following equation comes from at all, definitely let me know and I'll be happy to explain it in more detail. But remember, the basic idea behind superposition is that for a linear circuit, we can sort of turn off all of the sources except for one, find out our voltage or current due to that source, switch to the next source, so turn off all except for one, find the voltage or current. We do that for however many sources we have, and then we take the sum, and that's equal to the total response. So in this case, we'll have two terms because we have two quote-unquote sources, our VI and our Vout, and we would find that our V plus is equal to, so if we were to deactivate our output voltage, we would have from voltage division that V plus is equal to R2 divided by R1 plus R2 times the input. Similarly, if we were then to deactivate our input voltage and look at our V plus due to our V out, and we could use voltage division just like we did for our inverting Schmitt trigger circuit, we would find that that is equal to R1 divided by R1 plus R2 times V out. Okay, so here's our expression for V plus that we're going to use to get our relationship between our input and output. Just like with last time, because this is a bistable multi-vibrator circuit, it has two stable states, so we're going to have to assume something about the state. As a start, let's assume something about our low and high saturated outputs. Just like last time, for simplicity, let's assume that our VL is less than 0, so it's negative, and that our VH is greater than 0. And so that's not necessarily true, but we can go through with this sort of simplification in our initial derivation, and then once we have our equations, we can adjust that if needed. And we're also going to assume that the magnitude of these two are equal. So basically, if our VH is 5, our VL is negative 5. Okay, so we are going to have to assume a state as well. So let's start by assuming we have our VI less than 0. So assuming our input is starting negative, and we are also we have our circuit such that we have our output is V low. Okay, so, and again, we can keep in mind our basic comparator operations, but what we're interested in is our transition point. So for both of these cases, our transition point is now going to occur when our V plus is equal to 0. And so the reason for that is, of course, our inverting terminal is connected to ground. So our transition point is when the two inputs are equal. And so when this is equal to ground, or in other words, when it's equal to 0 volts, that's going to be our transition point. So we know our transition occurs at V plus equals to 0, and our VI at that transition point, we're again going to call our VTH. And so be careful not to confuse that with our threshold voltage or our Thevenin voltage. Hopefully, based on the context, it should be clear. But this is our high threshold, the same as we talked about for our inverting configuration. Okay, so let's take what we know and put it into this equation here. So we know this is our transition point, so we said that is V plus equals 0. So we have 0 for V plus. And we know that our input, VI, is going to be, at this transition point, is going to be VTH. So we're going to have R2 over R1 plus R2 times VTH. And we know that our output is going to be V low. So plus R1 divided by R1 plus R2 times V low. Well, so now what we can do is we can multiply both sides by R1 plus R2. So let's say we want to come in here and we want to say, I want to multiply everything here by R1 plus R2, which means we need to do it to this side as well. And so of course, that's just going to be 0 on the left still, but we can get rid of our denominators there. So what we can say is this is really R2 VTH plus R1 VL. Okay, and so we can then rearrange to solve for that high threshold, VTH, and we could find that that is equal to negative R1 over R2 times VL. And so again, we can sort of draw our plot. So let's draw our output voltage, V out, as our input voltage is varying. And we want to label our V high and V low, which we said are positive and negative respectively with equal magnitudes. And so now we've just defined this new VTH. So note in this definition, our VL was negative. So this value here is negative. And we also have this negative sign out front. So the two of those are going to cancel out. And our VTH is going to be positive. And so again, this might not always be the case, but for how we define things, this is how it would be. So let's go back up and look at what we assumed. So we were assuming that our VI is negative, and of course the transition point is going to occur as it's increasing. So we can say our VI is starting down here negative, and it's increasing, and nothing happens until we get to this transition point, and then it transitions high. So it's going to transition high, and then it's going to stay high from there on out. So we can put some arrows to indicate our direction for this curve here. Okay, so now let's consider our other case. So we can consider what happens when we have VI greater than 0 and our V out is equal VH. So again, our transition point is still going to be at V plus equals 0 because our inverting terminal is grounded. So transition point V plus equals 0. And we're going to call that transition point of our input VTL. Okay, just like we had defined previously for our other configuration. So again, we're going to come back to this equation here, and we're going to plug in sort of what we know in terms of our V plus, our input, and our output. And so just like with last time, we can get rid of that R1 plus R2 in the denominator, so I'm not going to bother writing it this time. But we know our transition point V plus is 0. That's equal to R2. Now this is our V transition low. And our output is equal to V high. So we can rearrange this to solve for our V transition low. We get that that's negative R1 divided by R2 times RV high. And so let me just point out again, this V high, earlier we said we're assuming it's positive. We have a negative sign. Resistors will always be positive valued, so that means our VTL is negative. So we can come back up here to our plot, and now we can add our VTL here. And so for our VTL, remember we were assuming that our VI is positive and our output is positive. So we're up here at V high, and then as our input is decreasing, it just keeps on moving this way. And so we can think of, we pass that transition high point, we're not going to transition high because we're already high. So nothing happens until we get to this V transition low, or V threshold low, and then we go low, and then we continue decreasing down here, our V input, but we stay at this low value. So along this red curve, we're moving from right to left then. So again, we still have this hysteresis, as we would expect. We didn't change the circuit fundamentally. The only difference is that now when our input is high, our output is also high. And when our input is low, our output is also low. And it's worth noting that just like with our inverting configuration, so for both inverting and non-inverting, the way we can design this hysteresis width, which again, this hysteresis width is the width between our 2 points here. So our width between here is our hysteresis width. And so we can adjust that width by playing around with our resistor values R1 and R2. Okay, so now that we've done that, what we're going to look at in other videos is how we can shift this hysteresis to the left or right. So we know by adjusting R1 and R2, we can stretch it out horizontally or shrink it in horizontally, but now we're going to look at how do we actually shift that left or right.